Good afternoon, everybody. Let's get started. My name is Steve Smith. I'm the editor of Ground Sport Worldwide. Thanks for coming. I'd like to introduce Todd Allen. He's the president of Allen Energy, and Todd will be speaking about next generation lead-acid batteries.
Thank you, Steve. Just a quick story. I was preparing my presentation last week, and actually I was packing to come on this trip on Sunday, and I'm telling my daughters, who are 7, what I'm going to be doing in Las Vegas, which includes this presentation. And I was saying I'm going to talk about a very old technology, lead-acid batteries, and how there's really not much to it. They were invented 150 years ago, and you and I could put together a battery right here if we had some lead and some sulfuric acid. And they interrupt me, like, "Daddy, no." I'm like, "What?" They're like, "Batteries weren't invented 150 years ago." And I'm like, "Yeah, lead-acid battery, I can't remember, it's like 1855 or something." They're like, "No, it was BC." Now they're 7, so I have no idea what they're talking about. So they get a book, and they say, "Daddy, the Baghdad battery," which I had never heard of. But I Googled it. It's a little clay pot that had some acid and an electrode, and they were making literally electricity back in something, they have to estimate it, but they found this battery in tombs. This is essentially what a lead-acid battery today looks like. The point of this slide is not to bore you with my children's stories at a GSE conference, but it's to just demonstrate that when we're talking about lead-acid batteries, it's pretty simple technology. We could, if we wanted to, you and me, or us as a group, we could start a lead-acid battery company and start building batteries next week if we really wanted to. There is some technology in lead-acid batteries, but it's always we're just tweaking it. In some ways, there's no free lunch. You can improve a lead-acid battery a little bit. So I can extend the life of a lead-acid battery by maybe putting a little bit more lead, making it heavier, making the plates thicker. I can improve the performance slightly. I can make it give you more capacity, more amp hours in the same cubic space, or I could give you the same amp hours but make the battery a little bit smaller. But again, we're talking about very, very minor improvements. I can make a battery that you don't need to water. I can make a battery that you only need to water a few times a year. And I can make a battery that is designed specifically for fast charging. And all these batteries are right now in GSE as we speak. But as my point being, these are just very minor improvements. So what I want to talk about today is maybe what would be a next generation, a revolutionary change in the lead-acid battery. I hope you guys saw the Corvus presentation because I agreed with every word. The lithium battery, I think what Brent said was the lithium battery is the best battery technology today. And I don't remember the exact word he used, but it was like barring economics. It's just expensive. But in terms of performance, I don't think you can beat it. But what I think you see is that there's a demand for high-performance batteries at a lead-acid price. Electric vehicle market, like cars, would be one of them. You can't put a $25,000 battery in a car because no one would pay for it. So you need some sort of technology that provides the power of a lead-acid battery at the price of a lead-acid battery, but at the performance of a lithium battery, or a fuel cell, or there's other technologies. There's a chance, now this is where Brent and I might disagree, there's a chance that lithium never comes down in price, that we never get to a lead-acid level, that it's always going to be significantly more expensive. So you have a lot of people now going, what about lead-acid? Why can't we have a lead-acid battery that has good performance? Well, there's a lot of reasons why you can't. First of all, they're huge. If you've seen a battery in your tractor, it's giant. It weighs a lot, 3,500 pounds. There's a problem with the chemistry and the way that you charge and recharge. It breaks down inside, it corrodes, it requires watering. A battery that doesn't require water has almost no life to it whatsoever. It has a relatively short life. With the lithium battery, Who knows exactly how long you're going to get, but let's just assume it's 15 years. Typical lead acid battery, you're looking at 5 years. It's sensitive to high temperature. It's also sensitive to low temperature. As you reduce the core temperature of the battery, you lose capacity in a dramatic way. Like you might only get half the capacity or 25% of the capacity if the battery gets that cold. And long charge time. Even with today's fast chargers, you can only go up to about 80% state of charge in a fast way. You can't get to 100% fast, even with the lead acid battery, even with the most advanced fast charger. So today I want to talk about what people are talking about doing, trying to do, actually putting into practice with lead acid to kind of come up with something that's high performing but still doesn't cost very much. And here are four. These are just four examples. I don't know what one would be the best. I don't know if any of these will ever find its way into an industrial application. But carbon graphite foam, ceramic bipolar, carbon electrode, and thin plate pure lead. I just picked these four because they're the most popular that I would say you'd find in terms of what people are doing with lead acid right now. Carbon graphite foam, if you're not familiar with what a traditional lead acid battery is, it's that plate on the left is an example of a typical negative plate. It's a thick lead grid casting, not much to it. In batteries, we're always looking for surface area. The chemical reaction isn't really taking place with the grid, it's taking place on the surface with a lead paste. So if you can increase the surface area, you're increasing performance and capacity. So this technology uses what would be called a carbon graphite foam plate. So it's a three-dimensional plate. The surface area is say 10, maybe even 100 times what a traditional plate would be. So what you have here is something that is lightweight, can have more capacity, has less internal resistance, doesn't get hot. We start seeing all those things that were wrong with the lead acid battery all of a sudden fixed just by changing the architecture of the plate. You also see a size difference. So you can see this is just an example of a 2-volt cell, traditional lead acid battery versus a graphite foam plate. Tremendous size and weight difference. And interestingly, they call it a 3D architecture. You can actually make the positive and negative plate out of a foam plate, and they call it the 3D squared, but that's a 2-volt cell. Another example is something called ceramic bipolar. Again, on the left, you see what would be a traditional lead acid cell, 2 of them. So you have isolated in a plastic jar, and then you connect them in series. A lot of internal resistance. So what they do is, instead of having these individual cells connected in series, it's not really important that you understand all the technology, but you stack these batteries and all the electrons move in one direction. Less internal resistance, less heat, much better energy density. Oops, sorry. You can see on the left that the way they stack them, it actually gets stacked a lot like what a lithium battery would be. And it's completely encased, so you could actually make it to where it could be waterproof. I don't think it would be necessary, certainly in a GSE application. This is of the four that I'm going to talk about, this one seems to be the less likely, the one with the most problems. Everything has to be sealed very, very well. You don't have the isolation that you do in a typical lead acid battery between cells. So if there's any seal issue, all of a sudden you're going to have an instant failure. Of the four I'm going to talk about, the carbon electrode I think is the most interesting and also the most simple. On the upper left, you see a typical lead acid cell, positive and negative plate, and then you've got a separator or electrolyte in the middle. On the upper right, you've got a supercapacitor. A battery, a lead acid battery, is great at storing a lot of energy, but it's not very good at delivering a high amount of energy. I forget what Brent said, but basically the battery would explode if you asked it to do 10 C for a sustained amount of time. A supercapacitor is really good at providing that burst of energy in a short amount of time, but not really good at storing a whole lot of energy. So someone came up with a really innovative idea and said, what if we combine the two together? So what they do is, you see on the bottom, for a negative plate, as you might say, it combines the carbon electrode and a typical lead plate, and that combination now provides a battery that can have a high output but also have a lot of stored energy. The people who make this battery would say that the supercapacitor takes all of the stress out of the battery, and so they also would claim, 15-year, 20-year kind of life. Interestingly, someone has also suggested this carbon electrode type battery using that foam plate, and you might get the best of all worlds in a battery that would have the absolute best performance possible. This is a picture. This is actually a battery put into, I think it's a Honda, maybe a Honda Civic. Another interesting thing about a carbon electrode battery is you can build it in the same facilities that existing lead acid batteries are manufactured. So we already have all the infrastructure in place to manufacture the batteries. Fourth and final technology, thin plate pure lead. Of the four, this is the most commercially viable. You'll see it in, you might even have heard of the Odyssey battery. Again, this is a deep cycle battery. Typically, you might find a 1-year warranty. This comes with a 4-year warranty. This is a picture of an automotive style battery, but what I'm talking about is taking this technology and putting it into an industrial battery that might eventually make it into a piece of ground support equipment. This is a really interesting idea too. Basically, you've got all these plates lined up in a cell. They said, well, what if instead of having 9 plates, like in a typical tug battery has 9 plate cells, what if we put 100, it has 40 cells, but if it has 9 plates in each cell to make a 500 amp hour battery, what if we put, instead of 9 plates, what if we put 20 plates or 50 plates or 100 plates? Like, we would obviously get more capacity, more energy in the same cubic space. So what they do is, it's called thin plate pure lead. There's a lot of advantages in the lead in that it doesn't corrode. It's also so thin, like the plates, they're like spaghetti. They're that thin, and you can pack a whole lot of them in. I would say this is the closest to existing lead acid technology. Again, we're talking about plates and acid, but we're just talking about squeezing more plates in and increasing energy density. Again, same with the previous one. This battery could be built in existing factories using existing manufacturing technology. Hold on. It also is available, this battery, here's a picture. This battery is this is a production battery, and you'll find it in all the applications listed here. I put this spreadsheet together. I don't want to get hung up on the exact numbers. It's mostly just as a comparison to show you what the potential benefits of changing the architecture of a lead acid battery would be. We go from having to water a battery to not having to water a battery. It'd be completely sealed, doubling the energy density, possibly even tripling or quadrupling the energy density, either making it 4 times the energy in the same space or making the battery maybe half or 25% the size. We go from temperature being a huge issue. Obviously, if you deal with batteries now, you know that they can't get hot, they don't operate too well when they're cold. That issue would go away with all the technologies I talked about before. Those go away. Life, right now you get 5 years from your lead acid battery, although I will say we replace batteries all the time, including this week where the battery is 11, 12 years old. So you can get, if you take care of a lead acid battery, especially in GSE, where the power requirement in a 24-hour period is relatively low compared to other like material handling type applications, you can get long life if you take care of your battery. But with these next generation batteries, we're talking about getting 10 plus years, maybe 15, maybe 20. No one knows, obviously, because we haven't put it in a GSE application yet. Recharge time, the fastest you're going to get out of the fastest fast charger, it's still going to take 3 hours to get to 100%. You can get to 80% really fast, but you're not going to be able to get to 100% very fast. Where, just like a lithium battery, you might be able to do it in about 30 minutes. And actually, what we're talking about on the right here, again, don't get hung up in these specific numbers because I'm just using them as more of a comparison. But this is like lithium type performance. The idea being we could achieve lithium type performance at a lead acid price. If we can accomplish that, that would revolutionize the battery industry. Just as a side note, I know my presentation, I got a call like 3 weeks ago from Michelle at Cygnus. She's my representative for the show. And she said, "Oh, I see you're presenting." And I said, "I'm presenting?" And she said, "I think so." And I'm like, "What am I presenting on?" And she's like, "I don't know, you're in the program." And I'm like, "Well, maybe you could send me the program and tell me what I'm supposed to talk about." I know my presentation was supposed to be on converting from internal combustion to electric. I decided not to talk about that because there is a presentation at 1 or 1:30 this afternoon on that exact subject, but I know it got canceled. So ironically, I probably should have included that in my presentation. I only mention that because if you really want to talk about converting from internal combustion to electric, that's one of my favorite subjects. I'd love to talk to you about it. You can call me or email me, come visit me, or I'll come visit you. We'll talk about it as long as you want to. If you have any questions about anything, though, I just wanted to give you my contact information. I'm also here exhibiting this week. And come talk to me in the booth. But thank you very much for your time. If you have any questions, let me know.
Does anyone have any questions for Todd? Well, he left us all hanging, you got to admit. I wonder, Todd, if you can give us a little 5-minute presentation on transitioning from diesel to electric?
Okay. Why not? It's a slam dunk economic model going from diesel to electric. If I wish I had my spreadsheet on this computer right now, there's about 10 line items of all the savings you'd get from going from any kind of fossil fuel internal combustion engine to electric. The payback is a year, 2 years. It's very, very short because of the fuel savings. I want to say, and I'm just going to guess, the diesel fuel in say a regular bag tractor in a typical GSE application where you're using about 250 amp hours a day, you might spend a couple $100,000 on diesel fuel over the course of the life of that tractor, where the comparable electricity is going to cost maybe $10,000 or $20,000. So obviously, it's a slam dunk to go to electric. So everyone should at least be considering going to electric. But there's a reason why we still have diesel GSE. And you wonder, well, why would we? If electric is a slam dunk, it's so much less expensive. And you can argue that it's less maintenance and it's easier. It's why. It's inconvenient. It's really easy to get low on gas and fill up and then keep going. It becomes a very serious problem when your battery dies because you can't just go fill it back up. So that means that it's a complete change in mindset when you go to an electric vehicle. And every application I've seen, at least initially and usually forever, the operators will let the tractor discharge all the way to zero. I even can tell you of examples where I get a call, there's something wrong with your battery, it's broken, we take it to the shop, which is expensive because it's a 3,500 pound battery, we got to extract it from the tractor, we got to transport it back to our shop, fix it. More often than not, there's absolutely nothing wrong with the battery. They just discharged it to 0 or less than 0% state of charge, and it's dead. They discharge it so much that the charger won't even recognize it to charge it. So the biggest thing you can do when you transition to electric is understand that you're going to have major mindset issues with operators. They're going to have to plug in their tractor. It has to get plugged in. The one thing I'm actually going to blog about. I'm going to write you a blog next week. The blog's going to be titled The One Thing. The one thing you need to do is plug your tractors in at night. If you plug your tractors in at night, that gives you all the time in the world to get it to 100%. If your battery is at 100% at the beginning of the day, in 99% of the GSE applications, if you start with the battery at 100%, you will not discharge it all the way during the day. It's only because the battery doesn't start at 100%, it doesn't get plugged in at night, that you operate it, you hit that creep mode, and then you have to plug in during the day. So you plug in for 15 minutes, you use it, you plug it in for 15 minutes. Next thing you know, you've got a battery that's extremely hot. And as we know, lead acid batteries, as they are today, really suck. And they're going to get extremely hot, and they're going to burn up, and they're going to die prematurely. And all of a sudden, that lithium battery that costs 10 times what the lead acid battery does starts to look really, really attractive. So that's a real roundabout way to talk about what you need to do. But I would say the one thing is to understand that you will experience problems. You are going to have a mindset issue with your operators, and the one thing you need to do is plug in at night, or at least plug in every chance you get.
Does anyone else have any other questions? Yes, Whitney.
Whitney.
Apologies.
You were going home, weren't you? Question I have, NiCad batteries, they always say totally discharge and then charge so the battery doesn't get a memory. Would you comment on that with your current lead acid
Yes.
batteries and what you think we should be doing?
So the question has to do with charging all the way or part way, or?
Yeah, they always say the battery will get a memory if you're
Yeah.
plugging it in
Right.
2 or 3 times during the day, whereas if you let it totally discharge and then recharge, it doesn't get that memory.
Okay.
That's true. Some battery technologies have a memory. If you remember cell phones a long time ago, if you, say, used them for 10 minutes and then you plugged in and charged it to 100%, and then you used it for 10 minutes and then charged it to 100%, eventually it would develop a memory which said, I only have to provide 10 minutes worth of power. That is not the case with lead acid batteries at all. But I will say this. They have, in some ways, the opposite problem. If you never charge it to 100%, the acid crystallizes on the plates, in which we call that sulfation, and then the battery dies. And the brief explanation is, and this isn't exactly technically correct, but you've got the electrolyte acid that's floating around. Either it's liquid or it's suspended somehow. When you use the battery, that acid goes into the plates and to create the electricity. And then when you charge it, the charger pushes the acid back out into the electrolyte. So if you use the battery and the acid goes into the plates, but you never fully push it out, it stays in the plate, sulfates. So in some ways, it has an opposite memory. If you never charge it to 100%, the capacity of that battery drops linearly just down. Next thing you know, the battery has 90% of its rated capacity, then 80, then 70, then 50, because that crystals are covering the plates that it makes it unusable. There's another question.
Things I think they need to do is build the technology into the units. They shouldn't allow you to only charge 10% of 10% of what it needs. You should have to go to a certain level, and then the unit should shut you down or tell you you have X amount of time, and not allow you to release that unit until it's fully charged. Because in the real world, that's not going to happen. You're not going to get people to fully charge it the right way. You're going to get...
No, I agree. I mean, if it was theoretically possible, I mean, I guess it's not theoretically, but if it were possible to force people to charge to 100%, or charge for more than 10 minutes. But
I mean, I think the technology's there to say, look, you're fully charged, now we're going to allow you to run this thing. Otherwise, it won't work. And when it's down to 80% or whatever, we're going to turn a thing on saying you need to bring it to the charge unit and you have to charge it. And it won't let you release it until you're back at 100%. And that's the only way you're going to gain control on it. Otherwise, it's not going to work.
Right. No, I agree. Let me say this first. As Brent was talking about in the Corvus presentation, lead acid batteries it's a stupid battery. So there's no intelligence in there for the battery itself with existing lead acid to be able to not provide power should you not get it to 100%. With a lithium battery, you could do that, or with the right controller. So with a lead acid battery, you would have to have that technology built into the tractor controller, and that is not very difficult to do at all. I mean, really, it's not. It's just a small programming change to where the tractor would require that 100% state of charge. Now, that would be so much better for the battery. And I'll give you an example. These batteries that I'm replacing after 12 years are typically in a conventional charge application where the customer is plugging in at night, it gets to 100%, and they don't have to opportunity charge all during the day. The reason why we have fast charging is because we've accepted that people are going to pull tractors off the chargers or not plug them in at night, so we have to create a solution so that, given that we are going to allow everybody to abuse the equipment, we're going to find a solution so that the equipment still works. I'm not saying that's right or wrong, just saying that that's the way it is. Batteries that are on fast charging, even though the fast chargers are very, very intelligent and do a really good job, you're lucky to get 5 or 6 years out of the same application. So now we've reduced the life of the battery because we've created a situation or an environment where we can have improper charging practices.